Hi, my name is Francisca, and this is my makeup project for test number 1. My partner Amber will be talking about another physics problem later on. So, the physics problem that I was assigned to me says two particles, one with positive charge Q and the other of charge 2Q, are separated by 3 centimeters. Part 8. At what point along the line joining the two charges is the field 0? Part B. If a positive charge Q is placed at this point and confined to the line, is it in a stable equilibrium? And we get a little definition in here. A particle is in a stable equilibrium if there is a force on the particle once it is slightly displaced, bringing the particle back to the equilibrium point. C. Is the particle of charge Q. If the particle charge Q is negative, is there a stable equilibrium point? So before I start working on the problem, I think it is important to go over some important concepts. I think the important concept for this problem is electric field lines, Coulomb's law. So an electric field is a space around a charged particle where the particle exerts electric force on the other charged particles. Because of their force fields, charged particles can exert force on each other without actually touching. Electric fields are generally represented by arrows. So we can see that in this picture. We have a positive charge and a negative charge. In a positive charge, the arrows go away from it. And in a negative charge, the arrows are coming in, just like it's demonstrated in here. Okay? So this is the electric field lines and the electric field. And before I forget, here is the definition back to electric field lines. An electric field line is an imaginary line through a region of space so that at every point it is tangent to the direction of electric field vector at that point. Okay? And we can see here that electric lines always points away from positive charges and towards negative charges. And here is the tangent, and each point in space the electric field is a vector is a tangent here. You can see this here. I also include this image of two positive charges because the problem talks about a positive Q charge and a positive 2Q charge. When there is two charges of the same sign, the electric fields don't touch, just like here. Electric field lines don't touch. In the electric field is the space between them, so they don't touch. So also something very important, like it says in here, electric lines are closer together where the field is strong, farther apart when it's weaker. So in here, in this space, the electric field is stronger because it's closer to the charge. As it moves farther away from the charge, it gets weaker. Okay, and we have the electric field formula right here. And this is due to a point charge. Electric field equals electric field equals a K, Q over R squared. So now we have the definition of Coulomb's law, and the definition of Coulomb's law states that the magnitude F of the force that each of the point charges Q1 and Q2 at distance R apart exerts on the other is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. In simple words, the force of attraction or repulsion acting along a straight line between two electric charges is directly proportional to the product of the charges and inversely to the square of the distance between them. So in here we have the formula where K is a constant, and we have it what K equals to, or it can also be 1, 4, by E0. So in Coulomb's law, we're trying to find the force, and force units are in newtons. Also, Coulomb's law talk about how forces of equal sign repel each other and forces of different sign attract each other. And this, going back to what we talked before about the electric field lines and the electric field, we can notice that here the lines don't touch, the electric fields don't touch because are the same sign. But let's say here the electric field lines go from positive to negative because there is a force of attraction. So I will start with part B because I wanted to see which if a positive charge or a negative charge will keep the system in equilibrium, and then I will work my way back to part A. Okay. So if we remember, the problem says that it is two charges, Q and 2Q. And now, if a positive charge Q is placed at this point, okay, so now we have so in part A, we're supposed to know at what point the system the field is 0. We don't know that yet, but we will find that out later. So let's say it is here. So the Q is a positive Q is charged in the point that the electric field is 0. This is positive Q prime. It's placed at this point to the line. It is a stable equilibrium. So let's see. To know if this positive Q prime charge maintains the system equilibrium, we have to see which forces are acting on every charge of this system. So we're gonna start with the positive Q prime. The positive Q prime and the 2Q will repel each other. So we have a force acting this way, and the Q and the positive Q prime will also repel each other, which is acting this way. Now we have a pair of forces acting in different directions. At the right location, these two forces can cancel each other out and possibly put the system in equilibrium. But we have to also look at the other two charges. We have to also look at the other two charges acting in the system. So let's look at 2Q and the charge 2Q. So 2Q will also have two forces acting on it. The force from the positive Q prime and the force from the Q. So the force of the positive Q prime and the Q will repel each other. Like this. And then the force exerting on the 2Q will also repel each other. So this will never cancel out. And therefore a positive Q prime charge won't work. The system is not in equilibrium. If I forgot, the system is in equilibrium when the electric field equals to 0. And for the electric field equals to 0, the forces must be cancelled out. So in here, the forces don't cancel out. So now let's see the case of a negative charge Q. So again, in a line we have Q, we have 2Q, and we have a negative Q prime at certain location that we will find out in part A after if we see if this case is the right case. So same concept, we have to see the forces acting on each of the charges in the system. Let's start with a negative Q prime. Negative Q prime and the 2Q will attract each other. And I will call this force F1. Now, Q and negative Q prime will also attract each other. And I will call this F2. Okay. So now we have a pair of forces pointing a different direction so they can cancel out and possibly put the system in equilibrium. But we also have to look at the other two charges and their forces. So let's do that. Now let's look at the forces acting the 2Q. So negative Q prime and the 2Q will attract each other. Because of Newton's third law, this force should be equal to this force. So I will call this also F1. And now the force exerted of Q and 2Q will repel each other. So this. Now we have the second pair of forces pointing in different directions, then they will cancel out. And finally, we can look at the Q. Before I forget, I'm gonna call this force F3, just to keep everything clear. Now we're gonna look at this. Q and minus Q prime will attract each other because of the law. Opposite signs attract each other. And same as before, this force and this force should be the same because of Newton's third law. So I'm gonna call F2. Now the force exerted by 2Q on Q will repel each other because both of them are positive. So this one goes this way, and this is F4. And this is our third pair of forces that point to different directions so they can cancel out. We can see that all the forces cancel out, nothing is add up, so everything is 0. So a negative Q charge at the right position that we will find out later will keep the system at equilibrium. Okay, let's go back to part A. In part A, we're gonna redraw everything. So we have Q, 2Q, so it says at what point along the line the two charges field is 0. So if the field is 0, electric field is 0, then the forces exerted must be equal to each other. And we know there is a third charge from the other questions that is somewhere in the middle. We will find the distance now. And we also know now that this third charge is negative. Right now right now right now the sign of the charge is irrelevant because we're still gonna use the absolute value. We already found the sign of the charge in part C, and it's negative. That's the only possibility that keep the system in equilibrium. So if we remember from last part, we have a force. Oh God. It's my first time doing this, so excuse me if I'm being a little messy. So we have the charge in here. We find out in the previous part that it was negative. Okay. And if you remember from last part, we have a force F1 and we have F2. The distance between Q and 2Q, 3 centimeters. And 3 centimeters equals 0.03 meters. So because of this, we can say that the distance between Q and Q prime is X. And the distance between Q prime and 2Q is 0.03 minus X. Now, if the system's equilibrium, force 1 equals a force 2. And we can express the magnitude of forces using Columbus law. So F1 will be equal to Q times 2Q divided by the distance between them, 0.03 minus X squared. Don't forget the K constant. And F2 equals a Q prime times big Q, which is also, we can also call it little q. To make things easier, I'm gonna call it little q over X squared. Now we had to set this equal to each other. F1 equals F2. I was forgetting the K constant over there. So K times 2Q all over 0.03 minus X squared equals a K Q times Q over X squared. Okay, so now that we set these two forces equal to each other, because the system, we need to find at which point the system's equilibrium, and when the system's equilibrium equals to 0, we can cancel common quantities out. So we're gonna cancel the K constant and the Q's, and this leaves us with 2 over 0.03 minus X squared equals a 1 over X squared. Cross multiply 2x squared equals 0.03 minus x to the square. Now we can take the square root to both sides, which is gonna give me which is gonna give me 1.414x equals 0.03 minus x. And I will continue it right here. Let me just make sure that the square root of 2 is the right. Let me just make sure. Yes, it's right. So 1.414x plus x equals 0.03. So now we have 2.414x equals 0.03. Solving for x, we get 0.03 divided by 2.414. X equals 0.03 divided by 2.414 equals 0.0124. So this is so now that we solve for x, we know that the charge is placed at 0.0124 meters from the other charges, and the charge is negative, and that's how the system is keeping equilibrium. I hope this was clear, and if you have any questions, please let me know. And I hope you enjoy it, or I hope I was clear enough. Like I said before, or maybe I didn't, this was my first time doing like a tutorial how to solve a question. So well, I hope you like it.
Hello, in this video, I'm going to be solving a problem related to magnetic field and magnetic forces from chapter 20. The focus of this chapter was one of the outcomes of this chapter was to calculate the net magnetic field at a particular point due to a compilation of current carrying wires. What is a magnetic field? A magnetic field is created when a charge is moving or a current goes through a conductor at all points. And a magnetic field is also a vector field. This is the problem I'll be solving from chapter 20 in our college physics book, problem 48. It says two insulated wires perpendicular to each other in the same plane carry currents as shown in figure 2064. Find the magnitude of the net magnetic field these wires produce at points P and Q if the 10 ampere current is A to the right or B to the left. This is the figure related to our problem. Here we have two conducting wires perpendicular to each other, and here we have the current equals to 10 amperes, and we have to find when A is going to the right and B is going to the left. And here we also see the distances from the x-axis and also from the y-axis. What is this problem about? This problem is about a magnetic field of a long straight wire. And they're asking to find the magnitude of the net magnetic field of a long straight wire. But note here that in this problem, we have two long conducting straight wires. The magnitude B of a magnetic field is given by permeability times the current carried by the conductor divided by 2 pi and r distance from the axis of the conductor. And we have here the permeability, which equals to 4 pi times 10 to the negative 7. I'm going to read the problem again. Two insulated wires perpendicular to each other in the same plane carry currents as shown in figure 2064. Find the magnitude of the net magnetic field these wires produce at points P and Q if the 10 ampere current is A to the right or B to the left. So the first thing we're gonna do is we're gonna list our known values. So we have the current 10 amperes. And we also have the in point P, we have two distances. We have from the x-axis, we have 8 centimeters. We convert to meters with the 0.08 meters. And we also have from the y-axis, 50 centimeters equals to 0.15 meters. We also have another current that will be our second current, that's 12 amperes. And at point Q, we have the same distance from the x and the y axes, 0.08 meters and 0.15 meters. So the problem asking first to find the magnitude of the net magnetic field the wires produce at points P and Q when the 10 ampere current is going to the right. So the current is going to the right, and by using our hand, the hand right rule, the current is going to the right, and we'll curl our fingers. The magnetic field is coming into the page, into me. So we use our formula B equals permeability times the current divided by 2 pi times r. So we have two currents and we have two distances. And as the current is going to the right, we're gonna add those currents and distance. So we can modify our formula. It will be like this. So at point P, we just have to plug in the values into our formula. So we have permeability that equals 4 pi times 10 to the negative 7 divided by 2 pi times the first current that is 10 and the distance distance 1, that is 0.08, plus current 2, that is 12, divided by the distance 2, that's 0.15. And we just have to put that in the calculator and solve for that. Here we can cancel out the 2 pi's, and we get 2 times 10 to the negative 7. We divide 10 divided by 0.08, and that equals 125, plus 12 divided by 0.15 equals 80. And that in total will give 4.1 times 10 to the negative 5. Our point Q we apply the same formula and we have the same value, so it gives the same magnitude. So for when the current goes to the right, the magnitude of the net magnetic field the wires produce at points P and Q will be 4.1 times 10 to the negative 5. Now in part B, the current is going to the left. So if we use the handwrite rule and the current is going to the left and we curl our fingers, the magnitude, the magnetic field is going out of the page, out of me. So we apply this formula. So we apply our known values. We already know permeability divided by 2 pi will be 2 times 10 to the negative 7. 10 divided by 0.08 minus 12 divided by 0.15. And this will equal to 0.9 times 10 to the negative 5. And that will be our magnitude of the net magnetic field the wires produce when the current is going to the left at points P and Q. And that's it for this video. Thank you.